Hello everyone. In this video lecture we began a study of chapter 17. Chapter 17 is a fairly long chapter. I've decided to divide it into two parts, part A and part B. I'm going to include the part A as part of the exam 1 material, and we'll see part B when it comes to the exam 2 material. All right. Chapter 17 involves a study of an important system in molecules that involves pi electrons. It's called a conjugated pi electron system. Well, what does that mean? To explain the meaning of that, let's start with some basics. An alkene contains one or more CC double bonds. If the molecule has two CC double bonds, we call that a diene. If it had three, it's called a triene, and so forth. Well, there are three possible dienes, and they differ with respect to the relative position of the CC double bond. If the two CC double bonds are adjacent to each other, sharing a common carbon, that diene is called accumulated diene. If the two CC double bonds are separated by a CC single bond, that's called a conjugated diene. If the two CC double bonds are more separated than that, that's called an isolated diene. What is a conjugated pi electron system? Well, that's any molecule that contains three or more adjacent p orbitals that are parallel and overlapping. Let's look at some examples. This cation is called an allyl cation, carbocation. We saw it back in chapter 2 when we began our study of resonance structures. The allyl carbocation, well, each carbon has a p orbital. All three p orbitals are parallel and overlapping. If you look closely, there are two pi electrons. Those pi electrons would be spread out over the two bonds. That is, spread out over the three p orbitals, a set of three p orbitals. This molecule here, it's a triene. It also is an example of a conjugated pi electron system. The most stable arrangement of this triene is where the molecule is planar. And in the planar arrangement, each alkene carbon has a p orbital, and all the p orbitals are parallel to each other. They're all parallel and overlapping. All right. So the first example of a conjugated pi electron system, the allocation has three parallel p orbitals. The second one has 1, 2, 3, 4, 5, 6 parallel, consecutive, overlapping p orbitals. This molecule, called an enone, also is an example of a conjugated pi electron system. In the enone's most stable shape, that would be a flat planar molecule. Each atom with a double bond has a p orbital, and all four p orbitals are parallel and overlapping. 1, 2, 3, 4. Now, in general, a conjugated pi electron system is more stable than a non-conjugated pi electron system. And this is largely due to the greater delocalization of electrons that you find in such system. Here's an example. Here is a conjugated diene, two double bonds separated by a single bond. In its most stable arrangement, well, that's a planar molecule. If you count p orbitals, that's 1, 2, 3, 4, that are consecutive, parallel, and overlapping. An examination of this dying, we find that the total of 4 pi electrons, that's 2 here, 2 here. Those pi electrons are not just delocalized in the double bond areas, as the drawing shows. They're actually spread out over these 4 atoms. There are, it's not shown, but there are 4 p orbitals, a set of 4 consecutive p orbitals that are parallel, and that total of 4 pi electrons are spread out over that set of 4 p orbitals. That spreading out over the p orbitals is a delocalization effect, and the more delocalized pi electrons, the more stable. This dying, conjugated dying, is more stable than this non-conjugated dying. In the non-conjugated dying, the 4 pi electrons, well, they're localized in the double bond areas here and here. All right. Now, why are conjugated pi electron systems important? All right. Now, we mentioned that conjugated pi electron systems are more stable than non-conjugated systems. And that's due largely to pi electron delocalization. Pi electron delocalization greatly lowers the energy of the species, which of course increases its stability. This stability will significantly affect the chemical behavior of the species. For example, if a molecular species is formed in the slow step of a reaction, and this species has pi electron delocalization, it will tend to form relatively rapidly in this step of the reaction, which in turn will increase the rate of that overall reaction. So if we have a reaction where we're forming a species that has pi electron delocalization, that's a conjugated pi electron system, it's going to be more stable, and if it's more stable, it will tend to form more rapidly. Now, let's look at this set of carbocations. Now recall, at this point in our study, we know of, well, 4 types of carbocations: tertiary, secondary, primary, and methyl. And we already know that the tertiary is more stable than the secondary, which is more stable than primary, more stable than methyl. And that's related to the number of electron-pushing alkyl groups, donating electrons to the positive carbon, stabilizing it. The more alkyl groups, the greater the electron push, electron donation, and the more stable the carbocation. Well, let's add to this series 2 carbocations that have conjugated pi electrons. First, let's consider this one. Now, we saw this just a couple slides earlier. It's called an allyl carbocation. Important to know the name of that. These 3 carbons here, each with a p orbital. P orbitals are parallel, overlapping. That's the name, allyl carbocation. Well, we mentioned that the allyl carbocation is an example of a conjugated pi electron system, and conjugated pi electron systems have enhanced stability, and that's due largely to the delocalization of the electrons. how stable is an allyl carbocation compared with an ordinary tertiary, secondary, primary cation? Well, the answer is shown here in this series. The allyl carbocation, if you look at it, technically is defined as a primary carbocation because the atoms in the molecule that are positive are primary carbons. It is the positive charge is located not on the middle carbon at all, but on the CH2 carbons. Those CH2 carbons are primary carbons, and everybody knows that a positive charge of primary carbons is not good. It should be unstable, but in fact, the allyl carbocation is more stable not only than primary, but also more stable than ordinary secondary carbocations. In a contest, in a stability contest with tertiary, it doesn't quite win. The tertiary is a little more stable. So the point to make, and this is worth putting in one's notes, that the allyl carbocation, even though technically it's a primary carbocation, has stability that's greater than secondary, but not quite as stable as tertiary. All right, now we define a new system here. It's called an allylic carbocation. By definition, an allylic carbocation has one or more carbon groups attached to the positive carbons of an allyl carbocation. All right, not the middle carbon here, but either of the end carbons. Now, most commonly, the carbon groups are alkyl groups, ethyl, methyl, propyl, and so forth. If you have a system, and if you have that type of carbocation with one or more carbon groups attached accordingly, that's called an allylic carbocation. Allylic carbocation is more stable than an allyl carbocation, and that's because it's got electron donating alkyl groups that feed electrons to the positive carbon. You can see here in this one, it's with one R group. That R is directly attached to a positive carbon. This R group feeds and donates electrons, stabilizing the positive charge. So understand what we mean when we say an allyl carbocation, and further realize that the allyl carbocation is more stable than an allyl carbocation. Interestingly, the allylic carbocation has an enhanced stability that makes it even more stable than an ordinary tertiary. So we have this series of carbocations, which I want you to learn, that the most stable carbocation that one can have is the allylic, which is more stable than tertiary, more stable than the allyl, more stable than secondary, more stable than primary, more stable than methyl. Keep in mind, too, that when we say allylic carbocation, I've got the representative one here with just one alkyl group. If I had one with two alkyl groups, now that could be an R group on this carbon. It could have a second R group on the same carbon, or it could have a second R group on the other CH positively charged carbon here. If you have an allylic carbocation with two alkyl groups, that'll be more stable than one with just one alkyl group. All right, now I want to begin a discussion of some chemistry which will shed light on the importance of conjugated pi electron systems. In this example, we will look at molecules undergoing a reaction, and we'll see that the presence of conjugated pi electrons will have a dramatic effect on the rates of reaction of those compounds. Okay, let's look at this first compound. This is called an allyl halide. Now, this group, CC double bond CH2 itself, is called an allyl group. You could add that along with your knowledge of ethyl, methyl, propyl, ordinary alkyl groups. That is, if an alkyl group has a double bond at position, it's called an allyl group. Well, with a halogen attached on the CH2, that's called an allyl halide. They're fairly common. The halogen here, X, can be bromine, chlorine, or iodine. The next one is called a crotyl halide. They're around, they're less common. That has a methyl attached to a CC double, attached to CH2 and a halogen. Notice there's an error here. There's too many hydrogens. That should be a CH3, CH double bond CH. Well, allyl halides and crotyl halides, let's look at their reaction typically in SN1 type reactions. What we find is that they undergo SN1 reactions very rapidly, even though they're technically primary halides. Notice the halogen is on a CH2 carbon. That's a primary carbon. All right. Allyl crotyl halides react very rapidly in SN1 reactions, even though they're primary halides. It obviously has something to do with the presence of the double bond. Well, let's go to the next slide to explain that. Well, I'm going to give an example of, let's see, this is a modification of an allyl halide here. This is a substituted allyl halide. Now, this is an allyl type bromide number 1. All right, it's an allyl bromide with a methyl attached. I want to look at the SN1 reaction of Roman numeral 1 compound with Roman numeral 2. All right, comparing the two, you can see that number 1 has a double bond in it, and number 2, Roman numeral 2, does not. If we study the SN1 hydrolysis of 1 and 2, this is basically reaction with water in an S1 fashion. One of the products is could be alcohol, or possible product is an alcohol. What we find is that 1 is like 1,000 times more reactive than 2. Right, 1 undergoes an SN1 reaction about 1,000 times faster than 2. Well, let's see if we can understand why. Well, to understand differences in reactivity, we always have to go back to the mechanism. We're told that the mechanism is SN1, and what is SN1? Well, it's a substitution reaction. That's 2 steps. The first step is the formation of a carbocation, and that's a slow step. So in order to understand why 1 is more reactive than 2, we look closely at its mechanism. Now, in the lower part of the slide here, I'm drawing out the mechanism. I'm actually showing just the first step in the mechanism. First step is the most important step. It's the slow step. That's what determines the reactivity. Well, 1 undergoing an SN1 reaction, forming the carbocation, it would form this carbocation. Now, do you see how we're getting this? Look up here at 1. If it's reacting so that it loses a bromine as a Br minus, if this Br breaks off with its pair of electrons as bromidine, it would leave a plus charge there in that carbon. That's one of 2 possible resonance structures. If you draw both the resonance structures, basically what you have is a carbocation with delocalized electrons and charge. And what I'm drawing here is the single dotted line structure representing those two resonance structures. Well, this single structure here, the dotted line structure, we recognize as a allylic carbocation, right? And you can remember from the series, the allylic carbocation is the most stable of all possible carbocations. So when one undergoes an SN1 reaction, it forms a allylic type carbocation, which is very, very stable. In contrast, compound number 2, undergoing an SN1 reaction, the bromine breaks off as bromidine, you form this carbocation. This is a secondary carbocation. Does this have resonance structures that I could draw? No. So this structure shown here is the secondary carbocation, no delocalization. In contrast to the carbocation that formed when Roman numeral 1 reacted, it has extensive delocalization of electrons and charge. It is an allylic carbocation, very, very stable. I think you can understand now why there's a difference in reactivity. 1 is more reactive than 2 because it forms a very stable allylic carbocation in the slow rate determining step, whereas 2 forms just a rather unstable secondary carbocation without any delocalization. Now, let me stress that this allylic carbocation here is an example of a conjugated pi electron system. Why? Because each carbon, these 3 adjacent carbons, when you look closely at it, would have a p orbital, and each p orbital is parallel, and those 3 parallel p orbitals overlap. It's a set of those 3 overlapping p orbitals that allows for the delocalization of pi electrons, there's 2 of them, and charge. And that's what largely stabilizes that. Now, what are the products of the reaction of 1? That's a good question, and let me answer the question. The question is, what would be the products of the SN1 hydrolysis of 1 or 2? Hydrolysis means just reaction with water. Well, if it's substitution, the implication is that the halogen is replaced by OH from water. That is, it's an alcohol product. For number 2, the reaction in water, Br, you just replace by OH from water, and that's an alcohol. That's a secondary alcohol. Just the one product here. You could also look at getting at by taking this carbocation and attaching where water covalently bonds and then loses a hydrogen ion in a fast follow-up step, and you're getting a secondary alcohol, one product.
Now, if you looked at compound 1 in the same light, if you did the same kind of thinking,
you break off the Br as Br minus. Plus charge forms there, and then bond the OH from water, and that gives you an alcohol. And that description, of course, is a description of just a single alcohol product. Well, the reaction of 2 gives 1 alcohol product. The reaction of 1 actually gives 2 products. All right, and there's a couple ways to explain that. In this slide, it's explained, but this looks initially fairly complicated. There is validity to all of this, and all this will make sense as I will explain it. But before I do that, I want to go to my whiteboard and to show you how the hydrolysis of compound 1 gives, in fact, two different products, two different alcohol products. All right, here we are at the whiteboard. What I want to show you is how you get two products from the SN1 hydrolysis of compound number 1. Compound number 1 is classified as an allylic halide. The SN1 hydrolysis means the reaction of water. Bromine gets replaced by nucleophilic OH from water. That gives an alcohol product. But how do you get two alcohol products from this? And as I show you this, I'm actually going to show you more of a general strategy about what to do when in the future you encounter an allylic substrate. So we know the reaction's SN1, and SN1, first step is the departure of the leaving group. We'll take the bromine and remove it as bromide ion. Use the curved arrow to show the Br coming off as Br minus. And then just draw the simple result of that. Now, the simplest and easiest thing that we would draw would be to show this carbocation, the plus charge on this CH carbon. Bromide ion has now been removed. Now, one of the things that we learned is that when you run across a molecular species, always stop and ask the question, can I draw resonance structures for that? This could be something that's presented to you by the instructor. It could be something that you see in an assignment in the textbook. It could be something that you write yourself. Whatever. That's what I want to do here. Can I draw resonance structures for the species? Well, the answer is yes. This corresponds to the resonance patterns of type 1. So let's just go ahead and apply that pattern and draw the other resonance structure. That means shifting the bond from the double bond one position. All right, now let's draw the result of that. All right, we would get this second drawing here. This is the second resonance structure. All right. Now, we also have learned that resonance structures aren't real species. They don't exist as such. They're drawings on paper. And the understanding is that if you take all of the resonance structure drawings, the real species is the blend or the average of those. However, I'm going to pretend that each of these drawn resonance structures is real. I'm going to take each one and do the reaction of each one and see what we get. I know that resonance structures don't exist, but I'm going to pretend that they do and follow through with that. And when we do that, this is a good way to actually figure out the different products for the reaction that you'll get. All right. So let's work on the first resonance structure here. In the SN1 hydrolysis, first step is forming the carbocation. Second step is attachment of the nucleophile, which is water. So that's what I want to do here. I want to attach water as a nucleophile. Okay, and so I'm going to draw a long curved arrow from the lone pair on oxygen and show it bonding to the positive carbon. Okay, now let's draw the product from that. It would be this. All right, now that's not our final product. The final product would be in the water portion having a loss of a hydrogen on it, like so. All right, and then draw the result of that. H plus comes off, and we would get this alcohol product. Okay. Now, this is the product that would form, assuming that the resonance structure was a real species and reacted accordingly. All right, now let's do the same thing for the second resonance structure. We're going to assume or pretend that it's real and have it respectively form the product, namely when the nucleophilic water bonds to the positive CH2 carbon. All right. So we're just going to take, as before, water molecule and have it bond nucleophilically to the plus CH2 there. Alright, and just draw the result of that. Alright, now we got to do one more final step, namely loss of hydrogen ion from the water portion of the molecule, and we're going to get our second product now. Namely that. All right, so there are the predicted products, the alcohol products, the two products you get from number 1. All right. And in the future, let me stress, when you see an allylic substrate, that is, it's got a CC double bond attached to a carbon bearing no leaving group, and it's under SN1 conditions, usually it will tell you that. What you want to do is write the carbocation it forms, look for resonance structures, draw the resonance structures, pretend each is real, and take each resonance structure, run that through the rest of the reaction. Carry out step 2 of the SN1 process with each of those resonance structure carbocations, we're assuming that they're real. And each one will respectively give a product that is one of the actual product it forms. All right, so let me go back to the PowerPoint slides. All right, now I'm back at the PowerPoint slides, and in this slide I want to show you an alternative way to show the formation of the two different alcohol products. All right, now if you recall that when allylic bromide number 1 reacted, it's an SN1 process, it formed a carbocation, and that carbocation is shown here. It's an allylic carbocation. So what I want to do is actually start with this allylic carbocation and take it through step 2, which is attachment of a water. All right, so here we go. Now here's the idea. I'm showing here a dotted line structure. This is not resonance structures. This is this represents the actual carbocation. It shows correctly which carbons have a positive charge. It's distributed on 2 carbons, the CH carbon here and the CH2. All right. Now, the water is a nucleophile. It wanders up to this allylic carbocation and it feels the attraction of the positive charge of 2 different carbons. It feels a pull from 2 different carbons. Well, depending. It's a statistical and reaction factor kind of thing, but part of the time the water will nucleophilically attach to this positive CH carbon here. I'll call that route B, and let's follow through what happens when this water nucleophilically attaches to that. The pi electron density here is pushed away, and so you end up with a double bond here. All right, now we have our water bonded to the CH. There's a positive charge of the oxygen. It's going to eject a hydrogen ion, and that forms the alcohol product here. That matches one of the alcohol products that we wrote in that on the whiteboard. All right, let's go back to the allylic carbocation reactant. Now, the other part of the time, the nucleophilic water will bond to this positively charged carbon here, and I'll call that route A. That nucleophilic water bonds to the plus CH2 that produces this. Of course, when it does that, the pi electrons in this portion or in this bond here are going to be pushed away, so the double bond ends up between these 2 carbons, and you get this species here. All right, this is going to, as we saw before, from the on the water part, it's going to eject a hydrogen ion, shown by the curved arrow, and boom, got this alcohol product. And this alcohol product would match the second alcohol product that we figured out on our whiteboard previously shown. All right, so this is an alternative way to show how you get two different alcohol products. When you're doing in an assignment or a quiz or an exam, I think the better way is to do it the way I did it on the whiteboard, right, rather than the way that we're showing here. But it's a matter of preference as well. All right, now turning the page to a different chemical reaction where the conjugated pi electron theme is also present. Now, let's just quickly review. If you have an alkene and you add halogen, you mix it with a halogen, chlorine, bromine, iodine, you expect an addition product. You expect a 1,2-dihalo product. That is, addition of the halogen will occur across the CC double bond. Now, indeed, that would be what would happen if you had taken this alkene, this is just propene, and halogen, X is going to be chlorine, bromine, or possibly iodine. You would see addition across the double bond. I mean, that's what alkenes do. They undergo addition. But something very interesting happens here. There is this kind of reality in chemistry that if you have a reaction and you change the conditions, sometimes you can create a completely different reaction, a completely different reaction pathway. And that's what's going to happen here. Instead of doing this reaction at room temperature, there's two possible conditions, alternatively I want to use. Either very high temperature, around 500 degrees, that would be like muffle furnace temperatures, or I want to do it under these conditions. I'm going to shine light through it, light from an incandescent bulb or ultraviolet light, and I'm going to keep the concentration of X2 low at all times. I'm going to maintain at low concentrations. How one does that, can be a mechanical challenge, but I don't want to have it just dump it in. I want to keep it at low concentration. If I use these two alternative conditions, there is a reaction, but surprisingly, it's not addition reaction. It is, if you look at it, it's a substitution. One of the methyl hydrogens is replaced by a halogen atom. The byproduct is HX. Completely different reaction. Kind of a surprise. Because you're going to always expect mixing a halogen and an alkene to get addition. But you don't get addition here. What's going on is this. The clue to this is this second, or rather the pathway where we use light. Shining light through something suggests the formation of radicals. Indeed, that's what's going on. By shining light or using high temperature, we're going to form radicals. And there's going to be a free radical chain type of reaction whose energetics is more favorable than energetics for simple addition of halogen to the alkene. So we get a completely different product. The energy of activation for the radical pathway turns out is lower than the energy of activation for the normal ionic addition. So you get a completely different product formed. Now, this product, as I said, it's a substitution. It's an important new reaction for us. We're going to show you how we can, an alternative way to do that in a controlled way. This reaction is referred to as an allylic substitution. Now, let me introduce some terminology. If you have a double bond in a molecule, a carbon attached to that double bond is called an allylic carbon. Now, I'm not able here to write that write out that word, but that's what it is, allylic carbon. Or you could say allylic position. As well, the hydrogen attached to the allylic carbon is called an allylic hydrogen. Now this reaction involves substitution of the methyl hydrogen, or you could say substitution of the allylic hydrogen by halogen. And this reaction is referred to as allylic halogenation. It's a new reaction for us, an important reaction, and we'll show you ways to carry that out. Now, there's a, let me make this for the comment. There's a problem if we want to carry this reaction to get allylic substitution by halogen, allylic halogenation. The conditions used here are not easy to carry out. High temperature is just not convenient. You have to use a special furnace. Shining light is not a problem, but the real challenge is keeping a low continual concentration of halogen. It has to be actually very low concentration. You could use, let's say, a rapid mixing and an addition funnel where you slowly introduce tiny drops of the halogen over time. And well, that's you get poor results with that. You got to get even better low concentration than that. So that this reaction, though, as I said before, is useful and important, right now it looks like it's not conveniently done. But chemists, realizing that, went to their drawing board and they figured out, they came up with a kind of designer allylic halogenating agent. Indeed, there's a couple of them they came up with. So that, and I want to show you that in the next slide. We're going to be able to accomplish allylic halogenation with one of these specialized designer agents. And there's one for bromination and one for chlorination. The one for bromination is called N-bromosuccinimide, abbreviated NBS. And here's the structure right here, NBS. All right. Now, if you have an alkene and there's an allylic hydrogen in it, if we mix the alkene and the NBS with, we do have to use a light. Peroxides will also work. You'll get your allylic bromination here. Now there's also a special reagent for carrying out allylic chlorination. There's the structure of that designer agent. It's SO2Cl2. It's called sulfuryl chloride. Well, let me show you in the next slide simple examples of using this new reagent. Again, your organic reactant is an alkene which has an allylic carbons in it. That is just a carbon attached to a double bond bearing at least one hydrogen. I'm using here propene as an example. I mix propene and the NBS with light, boom. The allylic hydrogen, the hydrogen from CH3, is replaced by Br. Now there's a byproduct. The bromine on the nitrogen of NBS gets replaced by hydrogen, and this is the byproduct that's removed when you do the cleanup and the workup, purification of the product here. So this is an example of allylic bromination using NBS reagent. Here's an example of allylic chlorination using sulfuryl chloride. You mix the alkene and the sulfuryl chloride with light. I mentioned also you can use peroxides in trace amount. You get the allylic chloride product. Okay, here's another example using cyclohexene, mixing it with NBS and light. Now, these are mixed 1-to-1. Now let's examine cyclohexene. You got to find the allylic position and the allylic hydrogens. All right. And these two carbons are allylic carbons. Each one has a hydrogen, so it's got two, notice, equivalent allylic hydrogens. Replacing any one of these produces this product here. This would be the allylic bromide product. Now, let me illustrate what's going on here mechanistically with respect to the allylic halogenating reagents. Let me use for illustration the N-bromosuccinimide, the allylic brominating agent. The allylic chlorinating agent works in a similar fashion. Now, try to make a complex story simple or a long story short. We've mentioned that radicals are involved. When there is a reaction involving radicals, recall what you will normally have is what's called a free radical chain mechanism. It has three phases: initiation, propagation, termination. Indeed, that's what plays out here. And I'm going to show you the pieces of that picture. So, all right. We start with the allylic brominating agent. I'm using, simplifying the drawing of it. The Q is everything but the Br. Let me just comment on that here. Here's N-bromosuccinimide. And this portion right here, that organic portion, I'm going to abbreviate with Q, all right? So here, this is the abbreviated structure of N-bromosuccinimide. This is a nitrogen-bromine bond. Now, light energy homolytically cleaves that, and you get two radicals, Q dot, bromine dot. Now, the active part here is the bromine dot, the bromine atom. Now, remember, one of the things that radicals do is to abstract hydrogen from a hydrocarbon. That's what the bromine atom does here. It removes this allylic hydrogen atom. Now, if you follow the half-headed arrows here, this pulls away a hydrogen. The odd electron moves over to form basically a carbon radical. Now, this carbon radical actually has resonance structures. I'm not showing the resonance structures, but I am showing a single dotted line structure for that. Now, I need to explain that a little better, so I want to now go to my whiteboard to make that a little clearer. Okay, I'm at the whiteboard now. I want to show you the reaction here in a little bit more detail. As we mentioned before, the bromine atom comes up and abstracts a hydrogen atom, one of the allylic hydrogen atoms. Now, when you're drawing the product here, the simplest thing is to draw it like this. Follow the half-headed arrows. You're going to end up with a one electron on that carbon. HBr is the byproduct. Drawing out the rest of the structure, you would have this. Okay, now this is a carbon radical, obviously. This is a special one, though. This is called an allyl radical. Reminds us of an allyl carbocation. Indeed, allyl carbocation had a positive carbon attached to a CC double bond. Here it's got a carbon. Oh, I've left out one hydrogen there. Excuse me. This has got a carbon with an odd electron, free radical carbon attached to a CC double bond. All right. So pay attention to this. This is something that's we want you to learn. This radical is called an allyl radical. Now, let's ask the question: can I draw resonance structures for this? For the structure. To answer that question, let's go back to the resonance patterns from chapter 2. All right, this is the PowerPoint slides where we introduced the idea of resonance structure patterns last semester. If you recall, there were 4 patterns, and we said we're just going to focus on number 1, 2, and 3. The number 4 we called attention to, and we said we would come back to that later. Well, now's the time to come back to it. Resonance pattern 4, you can see here, has an atom with a odd electron attached to 2 atoms of a double bond. You don't have to be carbon atoms. It can be really any elements. But if you have a structure that we're seeing here in this pattern 4, you're allowed to shift electrons, 1 electron at a time. If you follow half-headed arrows, you end up with this alternative structure. Note that both of these resonance drawings are equivalent resonance drawings, equivalent resonance structures. And so we're going to invoke that pattern in our allyl radical. All right, let's go ahead and shift electrons according to pattern number 4, Roman numeral 4. One electron shifts to the bond. The 2 shared paired electrons, 1 electron moves over to meet the first electron. The remaining electron shifts over onto the carbon, and you will get this second resonance structure. All right. Indeed, an allyl radical, you can draw 2 resonance structures for it. Note that these are both equivalent. If I took the top one and flipped it, I'd get the bottom one here. All right. Now, let me optionally draw the allyl radical with a single dotted line structure. What follows is this. Okay, here is it. We have the dotted line structure for the allyl radical. And we'd have a dotted line moving across the bonds here like so. Now there's a drawing challenge here. The end CH2 carbons each have basically half of an odd electron. Not to worry about that. Electrons are really clouds. You could have a partial cloud and so forth. Clouds are spread out. What we're going to show that is to put a dot in parentheses here and here. The dot in parentheses means it's not a whole dot, a whole electron. It's a partial electron, in this case half electron. Okay. Now, one other thing to point out here before we move on. Remember, we learned what an allyl carbocation is, and that if you attach a alkyl group to one of the end carbons, not the middle one, but one of the end ones, you get what's called an allylic carbocation. The same thing holds with the allyl radical. And I'm going to have to clear some space. Let me illustrate.
want to redraw the dotted line structure for the allyl radical here. Now, this is entirely analogous to what we did with allyl and allylic carbocations. If I replace one of the CH2 hydrogens by an alkyl group, I will get an allylic radical. So you're attaching an allyl group to either of the end carbons, not the middle one, but the end one. So let me do that now. Now this can be any alkyl group, ethyl, methyl, propyl, whatever. Just let it be represented by the symbol R. If I attach the R group, the alkyl group, to either of the end carbons of the allyl radical, I will get what's now called an allylic radical. All right. Now, this is your little lesson on allyl and allylic radicals. We'll talk about the relative stability of allyl and allyl radicals in just a little bit. All right, let me go back to the PowerPoint slides now. All right. So we're back at the PowerPoint slide where we're showing you the mechanism of allylic halogenation. All right, now this reaction here is the one that I played out in detail on the whiteboard. And this reaction, what I'm showing is the abstraction by a bromine atom of an allylic hydrogen to form an allyl radical using a single dotted line structure. Okay. Now, HBr node is the byproduct. The byproducts are often, we ignore them or we say they're not important. This actually turns out to be a very important byproduct. And here's what's going on. The HBr that forms in this reaction meets up with N-bromosuccinimide, the allylic brominating agent, and there is a two-step reaction. These are not radical reactions. It's an acid base followed by a nucleophilic substitution. It involves two steps. First, HBr donates a hydrogen to the nitrogen bearing the bromine, and then the bromide ion nucleophilically attaches to the Br there, pushing away the rest of the molecule, and you end up with this product. This is succinimide. This is succinimide in which the bromine is replaced by hydrogen, and Br2, the other product, the bromine molecule. Now the bromine molecule comes into play in a follow-up reaction. Now remember this allyl radical we formed up here. One of the things that radicals do, in this case the allyl radical, it abstracts a halogen, often from a halogen molecule. Here, this Br2 molecule we formed meets up with the allyl radical, the allyl radical abstracts a bromine atom from that to produce your allylic bromide product, plus an important byproduct, a bromine atom. Now, if you look at, there's actually 4 reactions. It's a set of 4 reactions, 1, 2, 3, 4. If you look back at the very first reaction, remember, it was a bromine atom that started this thing off by abstracting a hydrogen, forming the allyl radical, and followed by the next thing and the next thing and the next thing. Well, at this last reaction, we formed our product, but we regenerate a new bromine atom that can play the role that bromine did in the first place. It can meet up with a alkene product, abstract a hydrogen from that, followed by the next reaction, the next product, and yet a new bromine atom. We see we have a cycle of reactions that will occur over and over again. Indeed, if you back up a second, where light cleave the NVR bond homolytically, this is forming radicals in the system. It's the initiation. The sequence of these reactions here, which repeat and repeat as a cycle over and over again, we have the propagation phase. Well, of course, they're radicals in mixture. They're as before, they were going to be in very small numbers, low concentrations, but occasionally radicals find each other. When they do, they're going to immediately bond a couple. And I'm showing not all the possible coupling reactions. 2 bromine atoms can come back together to give Br2. A bromine atom could couple with an allyl radical, and so forth, and there are other radical combinations. But all of these play the role of killing off radicals, preventing them from perpetuating further propagation cycles. And that's why we call this, collectively together, these coupling reactions, termination reactions. That's the 3rd phase. So we have going on then, hopefully now familiar, free radical chain reaction, 3 phases: initiation, propagation, and then termination. All right. Now, in the whiteboard, I introduced the idea of an allyl radical. This is an example right here. And then the allylic radical, where if you take an alkyl group, whether it's ethyl, methyl, whatever, and attach it on one of the CH2 carbons, but not the middle one, you will get what we call an allylic radical. And we ask the question, what are the relative stabilities of those? Now, the answer is this. The studies show that measuring their energetics, that here is the observed series. And it's important to note this. I would like to say learn this. The allyl radical, interestingly, is even more stable than an ordinary tertiary radical. Now, that's a little different than what we saw with allyl carbocations and all. But here, the allyl radical is more stable than tertiary. Now, the allylic radical is more stable than the allyl because it's got a carbon group feeding electrons to the painful carbon bearing an odd electron, or a partial odd electron. So you attach those R groups, are going to stabilize the radical, and the more the better. In general, an allylic radical is in fact the most stable radical you could have, more stable than a allyl radical, stripped down, no carbon groups attached. The allyl radical more stable than tertiary, more stable than secondary, more stable than primary, and more stable than the least stable here, the methyl radical. All right, now I want to next go to the whiteboard and show you some examples, more examples of allylic halogenation. Okay, back on the whiteboard. I want to show you an example of predicting the product of an allylic halogenation. So let's take this compound. Okay, and I'm going to mix with it 1-to-1 mole ratio of an allylic halogenating agent, NBS, n-bromo-succinimide. Now we need, in all cases, to supplement that with light. Light is going to promote the formation of radicals. We're going to get a free radical reaction. It'll give us our desired allylic halogenation product. Okay, now predicting the product of this reaction is tricky. Don't try it on your own, because let me try to explain why. We've learned what an allylic carbon is, what an allylic hydrogen is. We've learned that NBS replaces allylic hydrogens by bromine. Now, a simple, simplistic way of looking at this is to examine this alkene and look for allylic hydrogens. Well, indeed, the methylene hydrogens, the CH2, qualify as allylic hydrogens, no question. These hydrogens here are allylic hydrogens. Now, a simplified approach would be to replace one of those CH2 hydrogens by a bromine and write that for your product. And then walk away, go on to the next problem. However, if we did that, here's what would play out. You would be half correct because there are actually more than one allylic halogenation products. And I want to show you what to do when you encounter a case like that, and so that you will get the correct products when there are more than one. And here's basically what you're going to do. Okay, now you need to think a little bit of mechanism here. Mechanistically, now you don't have to play out the whole initiation, propagation, termination scenario. The important thing to remember is that the most important step in the mechanism is the abstraction of hydrogen to form a carbon radical, namely an allylic radical. So we'll do that here. What we're going to do is just remove one hydrogen from CH2 as an H atom to give us the allylic radical. Just take off the H atom, leaves you with a C dot, and just drop the rest of the molecule. Now that's the key reaction to write. You don't have to put anything else in. And get on paper there the structure of this free radical that forms. Now, we learned about a new resonance pattern involving radicals, and following through with the thing we always do. If we have a species, ask the question: can I draw a resonance structure for that? Can I draw resonance structures for this? Well, the answer is yes. It's invoking that new pattern 4 type, where you have an allyl or allylic type radical. So the answer is yes. We can draw resonance structures, so let's just go ahead and draw that. Now, in this case, this means shifting single electrons using a half-headed arrow. Right, the odd electron shifts over into the bond. Paired shared electrons, one electron shifts over to the bond to meet that first electron. The other electron of the pair shifts over onto the atom, the CH2, and here's what you would get for a second resonance structure. Okay, there it is. you have these two different, my electron isn't very well drawn, so I'm trying to correct that. Okay, I paused the video and fixed my drawings up a bit. I removed the half-headed arrows so you can see the C dot properly in the left resonance structure, and then I've got a better dot drawn on the right resonance structure. So these are the two resonance structures that you would draw for the radical product that forms. I'll repeat again that resonance structures aren't real. They're drawings, and the real species is the combination hybrid of those. But in this case, we're going to proceed as we did with the allylic carbocations. I'm going to assume that each radical is real and accordingly write a product for reaction of that. All right, so let's look at the left resonance structure. I know you're not real, but I'm going to assume you are. The important thing, reaction here is the abstraction of a halogen atom from a halogen molecule. It's a bromine molecule that forms in the propagation cycle. You don't need to write its formation, just to realize that it's there. That's the key reactant. That Br molecule is there, and that our radical is going to abstract a bromine atom from that bromine molecule, just as I'm showing here. All right, and now just draw the product of that, the organic product. There we go. This is one of the predicted allylic bromination products. All right, now let's turn our attention to the other resonance drawing. We're going to pretend that it's real and allow it to react. It's going to react in the same way, abstracting a bromine atom from a bromine molecule that forms in the process. So, using my half-headed arrows, you would get then this allylic bromide product. Okay, and let's see here. There's a correction to make in just a second. All right, too many hydrogens there. All right, and there we have it. Assuming that each resonance structure that we draw, each allylic radical type drawing is real, and letting each one react, that's going to point us to, in fact, the correct product. And here we have it. And we are going to, if you take a look at these two products, just going to circle them, writing down these two products. Notice they are clearly different, and these are the two organic products are going to form, the two allylic bromination products. Now, one of them corresponds to the what you get when looking at it in a simple-minded way, without going through the details, namely that one you get by replacing the CH2 allylic hydrogen by bromine. The other one wouldn't be obvious, the second one that forms here. And now, the amounts that form, they're not equal, they're in comparable amounts. The percentages of each are beyond the scope of our coverage, just to understand that they're both going to form. So that here is the I think the key to this. Let me clear some of the board space first, and allow me to do that. All right, now in this particular reaction, when you think it through, you see that you get two products. In the previous examples, however, we got only one allylic halogenation product. Why the difference? Well, it's this. When your alkene starting material, if you form the allylic radical from it, and if it has resonance structures and you draw them and they're equivalent, you only get one product. It's only when you have two or more non-equivalent allylic radical resonance structures where you're going to get more than one product, as we have in this case here. These two resonance structures are not equivalent. They lead to different products. All right, and so in contrast to that, let's take a look. Let's look at this example of allylic halogenation. We have an alkene. And you notice now that in the cyclopentene ring there are two allylic hydrogens here and here. But you're only getting one allylic bromination product, namely that. A couple ways to look at it here. Both these allylic hydrogens are equivalent. They give the same product, so you're only getting one product. And as well, the other way to explain it is when you write down the two, when you write down the allylic radicals that form, or rather the allylic radical and the resonance structure. Let me go ahead and do that. All right, now that's taking this, let's say, this hydrogen atom away and getting this. When you draw the resonance structures for that, all right, applying our pattern 4 now, that would give you this other resonance drawing. All right. And here's the difference, here's the contrast. In this particular reaction, the two resonance drawings that we draw are equivalent. These are equivalent resonance drawings. Equivalent. Resonance structures. They're only going to lead to one product. Both of them lead to the same product. So the general rule is this: if you have an alkene with allylic hydrogens, write the simple allylic radical structure for it. Check to see if there are resonance structures, draw the resonance structures. If the resonance structures are not equivalent, you're going to get more than one product. If the resonance structures you draw are equivalent, you're just going to see one allylic halogenation product. All right. Now this basically concludes my Part A for Chapter 17. Let me just say a few things to kind of wrap up things here. This is a summary of the important points in the Part A of Chapter 17. We need to understand the meaning of a conjugated pi-electron system. No meaning of conjugated pi-electron system. Now, it's any molecular species. It can be a stable molecule. It could be an intermediate of some kind, a radical, or cation or anion. Any system that has 3 or more consecutive, parallel, overlapping p orbitals. In that set of p orbitals, there's going to be electrons. They will be spread out over that set. And understand, too, then, that if you have a conjugated pi-electron system, this is very stable. Largely due to just the delocalization of electrons in the system. Now, there are other factors that contribute to that stability, and I have commented on that in this video lecture, but maybe this can come out in the discussion board. So anyway, knowing the meaning of a conjugated pi-electron system and that it has enhanced stability, there are basically in the Part A of Chapter 17 the 2 reactions that you want you to understand. And so we say the reactions. The SN1 reaction of an allylic substrate. Now, this could be allylic halide, it could be allylic tosylate. In the SN1 reaction, it forms an allylic type carbocation, which is very stable, that makes this reaction fundamentally very, very fast. Allylic substrates in an SN1 reaction are going to be very, very reactive. To understand that, and then be able to predict the product or products from that reaction. And 2, allylic halogenation. This is a reaction of an alkene with 1 or more allylic hydrogens reacting with an allylic halogenating reagent, either the N-bromosuccinimide, NBS, or the sulfuryl chloride. Both of them work in the presence of light, and fundamentally the reaction pathway is a free radical kind of pathway. And to be able to understand that in allylic halogenation, you can get more than one product, more than one allylic halogenation product. As well, in the SN1 reaction of an allylic substrate, you can get more than one product. Now, with reference to, in fact, both reactions, just kind of an overview. Here is a general structure for an alkene with 1 or more allylic hydrogens. You could say an allylic system. We have to do some updating in our knowledge base, and let me explain. Back in chapter 9, I guess it was, we learned that when you have a carbon-carbon double bond, the reaction that you're going to think of is addition. That, we pointed out, is the major reaction of alkenes, and you see an alkene, we want you to think that, to think addition. Now this is an exception, though, to that pattern. All right, this is an exception to the pattern. And you can see the exception just from, well, you want to think about it in this way. Just because you see a double bond doesn't mean it's addition. There's two situations now. If you have your alkene and an allylic halogenating reagent, that is, if you've got this and you've got either NBS or sulfur chloride, SO2Cl2 plus light, seeing that allylic halogenating reagent and different conditions is a signal that it's not addition, right? Not addition. And then, carry out the appropriate correct reaction for it. Also now, if you see an allylic substrate, where L is either a halogen or a tosylate, you will see with it something that will ordinarily not add to double bonds. You're going to see with it some kind of nucleophile present, basically. In our example, we saw water. So if you see an allylic substrate, that is allylic halide or allylic tosylate, and a nucleophile, well, the nucleophile isn't an ordinary adding reagent. This should be a tip-off, a signal that alkene is not undergoing addition. Instead, it will undergo allylic substitution, where the leaving gets replaced by nucleophile. And so, yeah, if you kind of add that to your strategy in figuring out reactions, I think that'd be very helpful. So just quickly summarize. You see an alkene, ordinarily, yeah, think addition. The exceptions to that are if you have an allylic substrate, allylic halide, and a nucleophile, it's not going to be addition. It's going to be substitution, where else it'll always be SN1 substitution. Or if you see an alkene and reagents that are not regarded, you're not going to regard them as adding reagents. They're allylic halogenating agents. Pay attention to those with light present. That will be a case of not addition. It will be rather allylic substitution, allylic halogenation. All right. Thank you very much for your attention. And as I say, this will complete Part A of Chapter 17. Part B video will be up later, and all that material will be part of Exam 2. Thank you very much. Bye.